Did you want
All right. So
Yeah.
we're
to?
going to
Never collected the 100.
we're going to continue with 1.3. Most of it is again completely reviewed. I shouldn't be able to tell you anything new here, and it's probably going to be a little bit annoying with me going over everything again. But we're going to go over something. Not in as much detail as I normally would, because I really think you guys should have this under control. It's about those quizzes. More than a handful of people got over 100 on the quizzes, so now I'm thinking, way too easy. I need to I can't have. I got people with 109% average in the class. Like that, no, I can't be known as the easy professor. Like the next quiz. We're going to continue with 1.3. We were talking about linear models, as you may have remembered. Just want to remind you of a couple things, just to bring a couple things to your attention. Because a large part of this class is just knowing how to interpret mathematical statements, or getting regular statements and interpret them in a mathematical context. So you kind of need to know when you should use a linear model. And at least for this class, there are going to be two main instances that you know you have to use a linear model. One is that you're specifically told to use one, right? That's smart. You are told to do so, right? So that brings the example to mind of the hot dog stand example, where I actually told you that the number of hot dogs and the price have a linear relationship, right? So that you'll see phrases like, they have a linear relationship. You might also see something like directly proportional. I won't use that phrase often, but it's just in case you see it somewhere else. You see something like directly proportional. It also tends to be a linear kind of thing. So a problem might just tell you to make this assumption, and the reason behind that is sometimes you'll encounter situations where you're not sure what's the best model to use, and so you kind of use the simplest model that you can think of to approximate what's happening, and then you kind of check if it's working. So a lot of times if you think something might have a linear relationship, you might actually try to model it with a linear relationship, and then actually see if the reality matches with your model over time, right? So sometimes you will be told, actually be told to make this assumption, and there are cases where you might make this assumption, but for now you don't have to worry about that. I will tell you if it's not immediately clear from the context. Sometimes when you will not be told that you need to use a linear model is in the following case, which brings to mind the example I did last time with the car rental company, right? You are measuring a quantity. That is changing, meaning it can be increasing or decreasing by a fixed absolute amount. Right? Absolute is to distinguish it between something like relative amount or percentage amount. Absolute means it's just the magnitude of the thing that's changing. So for example, in that car rental example that I gave you, where I told you that you pay a flat fee to rent the car, but then you get charged like $2 per mile or something, I believe it was. It's always $2 per mile. It's a fixed amount that keeps increasing the cost of the rental, right? So that's just whenever you have a fixed amount that's in value, it's fixed. It's always going to be $2 no matter what. After some period of time, it's increasing by a fixed absolute amount over regular intervals. So it could be in terms of time, could be in terms of distance, could be in terms of something else. But after a certain amount of things happening, a certain amount of intervals happening, it's always increasing by this fixed amount. And so if you can read a word problem and realize that situation is happening, then I don't have to tell you that it is a linear model, and I won't tell you it's a linear model. You just kind of have to figure out, based on the wording of this problem, it seems that it's changing by a fixed value. It means a straight line is the function I should be using. So those are the two main situations in which you would know that you need to use a linear model. Okay? So I will either tell you, or you realize something is changing by a fixed absolute amount. And in the next section, we'll look at a different kind of change here that's going to be very important. But that's the two main times you want to use a linear model. The hot dog example would cover this situation, and the car rental example would cover that situation if you want to see examples of that, of how a problem might be worded. So now, a linear model means the best function to use is that of a straight line. So let's remind ourselves about lines. Tell me about the equation of a line, like a general form.
Y equals mx plus b.
Y equals mx plus b, right? This is one way that you can describe the equation of a line. This is called, by the way, the slope-intercept form. So if I ever ask you, find the equation of the line in the slope-intercept form, it means I want you to write your answer down in this form. M and B are, of course, constants. X is your independent variable, Y is your dependent variable. This is where M is the slope, and B is the y-intercept. Right, so the picture you can imagine, something that looks like that. The point it passes through here, that's your B. That's called the y-intercept because that's where it intersects the y-axis. And this is the horizontal, that's called your x. This intercept here, by the way, is called the x-axis, the x-intercept. And that B is called the y-intercept. So you can describe an equation of a line in that way. The slope n becomes a measure of the steepness of the line. Okay. And we can either be given n. So for example, in the car rental property, technically I gave you the m value, but I didn't say, oh, this is the slope. That $2 per mile that you're being charged, obviously when you kind of put that into the equation, you realize that was the slope. So you need to recognize when you're being given n. You can either be given it, right, so someone's telling you how something is changing by a fixed amount, and that will actually be your m value. So you can either be given m, or we can find it given 2 points. Meaning we're given 2 instances of these related variables and their values at those instances. So here given 2 points x1, comma y1, and I believe I asked this on the quiz, which is probably a dead giveaway, but x1, y1, and x2, y2, we have m would be equal to what in this case? y2 minus y1 over x2 minus x1. This, by the way, is just a measure of the rise over the run. And in general, it doesn't matter what order you do things. It doesn't matter which point you pick to be your x1, y1 and which point you pick to be your x1 and y2. Just make sure they line up correctly, right? The x and y's for each individual point are right on top of each other, and there's a subtraction in the middle. And that's just a measure of the rise over the run. So you can imagine if this were an x1, that were an x2, that would be a y1, that would be a y2. Then this distance here, that's your rise. That's just a vertical distance, which you can find that distance by taking this number, subtracting that number. That's your y2 minus y1. And here, this guy is called the run, and that would be equal to your x2 minus x1, right? So horizontal distance, you take the right minus the left to find the horizontal distance. And that's a measure of the steepness of the line. Given a point, let's say we're given one point, x1, y1, and n. You can also find the line using this formula: y minus y1 equals n x minus x1. That's another form of the equation of the line. This is called the point slope form. So to actually find the equation of a line, and it's okay to leave it in point slope form, you literally leave it in that form. Which a lot of times I think it's more convenient to use that guy, because you don't really, if you're using the y equals mx plus b, usually you have to go separately and find b, and then you have to come back and plug it in. Here everything is all condensed for you, and you can solve for the y if you want without back substituting. But it's usually going to be a matter of preference for which one you like. Of course, the sign of m actually matters. So for a straight line, there are actually just 4 possibilities for which situation you can be in. You can have a line that moves up as you move from left to right. You can have a line that moves down as you move from left to right. You can have a line that stays steady as you move from left to right. And you can have a line that does nothing as you move from left to right. These are 4 different situations that you can have for a straight line. What can you tell me about the sign of the slope in this situation?
It's positive.
It's positive. Slope would be greater than 0 in this case. Okay? So that means the slope is positive. What can you describe to me about the behavior of a line with a positive slope? We actually talked about this last time. What is the phrase that we would describe this line about how it's changing? Yeah?
Increasing?
Increasing. Increasing means getting bigger, getting larger. Okay? So whatever quantity this line is measuring, you can say over time it's getting larger. Right? This would be an interpretation of that. Right? Now if you model a quantity with a straight line, and in this case the slope would be negative, you can realize that the quantity that this is measuring is decreasing. Or in other words, it's getting smaller. In this case, your m is equal to 0. That's when you have a horizontal line. And this means staying constant. It's not moving. This one here. What's the m value for a vertical line?
Undefined.
It's undefined. So the slope here is undefined. And this means it's not a function. So for that one particular input is the only one that's valid, and we can have any y value for that function. And last time I was talking about how that simple idea of knowing that, oh, A straight line that moves up as you go from left to right has a positive slope, and that means increasing. And I was talking about how that leads to almost half of calculus. Well, not exactly half, but a very big and important part of calculus called differential calculus. And right now I'm going to give you another part of that puzzle of the interpretation, but this is one of the main things that you should just know about slope. But so far I don't think I've said anything that you're not aware of. And now I'm going to say something that you're probably also aware of, but I wouldn't be surprised if you're not aware of it. So I'm just going to tell you. An interesting interpretation of slope. Now, if you ask an algebra student or a pre-calculus student, what do you think of when you hear the word slope? They'll probably respond to you in that formula. Oh, it's y2 minus y1 over x2 minus x1. Or, oh, it's something how we measure the steepness of a line. I want you to think of it as another way. And there's another way that a calculus student would think of slope, and that's the way I'm going to introduce to you now. And I'm going to kind of segue into it with an example. That it should make it kind of obvious how I want you to interpret slope. Suppose we're measuring the distance traveled by an object. And just me by measuring distance of the object, it yields a graph, right? Let's say that graph happens to be a straight line. So I'm measuring an object such that if I measure its distance, let's say for argument's sake I measure it in terms of miles. And I'm measuring it with respect to time, for argument's sake, let's say I'm measuring hours. Now let's say the object behaves this way, right? So the object is moving, it passes a certain point, which I consider position 0, and I start my stopwatch, and I'm measuring the distance of the thing from that point on. So it's at the point 0, 0. And its graph ends up looking like a straight line if I plot the distance after time, as time is going on, and I realize that it's covering, again, a fixed amount of distance per unit time. That's why I would give this line. And let's say it travels at a distance of 80 miles over the course of 2 hours. Question 1. What is the slope of this line?
Is it 40?
Slope is 40. How would you get that?
80 over 2.
Take 80 over 2, right? Which is basically the rise over the run. Right? Or you can think of it as y2 minus y1 over x2 minus x1. But you get 80 over 2, and you get 40. Question 2. Interpret that number. What does that 40 mean in this context?
The rate of change.
Rate of change? Why would you say it's rate of change? It's a very strange way to say it.
Because it's how. Because it's delta y over delta x, so it's the speed that it's going.
Speed, okay. So that's like a language that most people would understand, even those that didn't take calculus. You tell someone, the average Joe on the street, oh, it's a rate of change. What are you talking about? It's actually telling you a speed. How do you know it's telling you a speed? Yeah?
Is that distance over time?
It's distance over time. You see, if I give you this graph, then to you it's just y2 minus y1 over x2 minus x1. But then I slap an interpretation on these variables, and now these numbers actually have meaning to them, right? The top numbers measure a distance, which is miles. The bottom number is measuring a time, which is hours. So the units you end up getting is miles per hour. And we normally interpret that as speed. Or, strictly speaking, it's velocity here, but you get what I'm saying. The units of the slope in this situation actually gives us, I can interpret it as the speed at which the object is moving. So you finding that 40 is not very interesting, but the interpretation is what I want to get at. The fact that I can actually interpret the slope in terms of some other real-world kind of criteria. But since we're math people now, we're going to want to make this abstract. We're going to think abstractly. There's nothing special about miles or hours, right? These are just labels that I put on a picture, right? The questions I would find the slope in exactly the same way if you didn't know what these numbers were. There's nothing special about what the interpretation I gave to the variables. However, the idea that it's measuring, as she said, a rate of change is a more broadly applicable kind of characterization. In other words, from now on, as a calculus student, when you hear the word slope, you're not going to think y2 minus y1 over x2 minus x1. Well, you will think that that's a part of it, but that's not all you're going to think. You're going to think of the slope as a measure of how fast y changes with respect to x, right? And in fact, my x and my y can have almost any interpretation I want, okay? Where x and so in here I interpreted the y as a distance and the x as a time, but there's nothing particularly special about that interpretation. Where x and y can be given arbitrary interpretations. In other words, I didn't have to choose distance and time. I could have chosen number of products sold over time. I could have chosen number of products and price. I could have chosen any two variables. And how you'd interpret the slope is how one is changing versus the other, right? How fast one is changing versus the other. E, slope, is a measure of the rate of change. The dependent variable in relation to the independent variable. Furthermore, sign interpretation holds. This means if the slope is positive, this means the change is an increasing one. Right? The fact that I got a positive 40 miles per hour sort of means that the distance was increasing as I'm moving from this point. If I measured the slope of some object that I was measuring the distance and I got a negative number, I would think of it as the distance decreasing to the point. But this is a very important interpretation for slope. And in terms of calculus, this is what is going to kind of force us into the study of calculus, kind of. The fact that we can interpret slope as a rate of change. We can interpret it as a speed. Any questions so far? Are you guys getting what I'm saying, or am I just? You guys kind of get what I'm saying? You can, if a line is measuring some variable versus another variable, the slope of that line, you can think of how fast one variable is changing in relation to the other, right? And so from now on, that is a new interpretation that you should have when you see slope. So yes, slope is y2 minus y1 over x2 minus x1, and yes, it's a measure of the steepness of a straight line, but that is where an algebra student would end the conversation. A calculus student will think further. The calculus student will say, oh, it's also a measure of rate of change. And also, the sign will tell me the kind of change that's happening. So if I measure a slope, and I realize it's positive, it means that the dependent variable is increasing with regards to the independent variable. If I measure a slope and it's negative, it means that the dependent variable is decreasing with regards to the independent variable. And we'll stop there for now. So we've just completed 1.3. I didn't really say anything strange in terms of formulas or content, but it's very important that that last thing that I mentioned, your interpretation of slope, is something that you now have stick with you. It's going to be very important that you can interpret slope in this way. So the homework for 1.3 is due on Friday. We're going to move on to 1.4. Again, I don't really want to spend too much time on this section either, because you can't fully study without knowing about some other functions that I didn't tell you about.
There's no 1.4 on the syllabus. 1.4 in the book is polynomial models and power functions. And
1.5.
Okay.
We skipped 1.4. Talking about exponential models, right? An exponential function is one of the form y equals a to the x. A is constant, so it's a number. X is the independent variable. Example, y equals 2 to the x is an example of an exponential function. Y equals a half to the x is an example of an exponential function. Y equals x squared, not an exponential function. Right? Y, the base is the constant, but here the base is a variable. Okay? So don't just think of anything raised to a power as exponential. That's not what it means. If the base is a number, it's a constant, and the power is a variable, you can think of it as exponential. Okay? And this is a special kind of function. So we're going to talk a bit about this function. Let's see. Maybe we can fit it here. Let's do some important facts. 1. Exponential functions obeys the laws of exponents. So all the rules for the laws of exponents, they apply to exponential functions. So for example, if I have one function where x is the independent variable and another function where y is the independent variable, then I can actually multiply these two functions together, and the result is going to be I add the powers. Right? So I can get a new exponential function by multiplying two known exponential functions. Similarly, if I have one exponential function divided by another exponential function, they have the same base, then I subtract the powers. Similarly, at any point where my independent variable hits the value 0, it will give me 1. And of course, I'm saying my a is greater than 0. So that doesn't actually have 0 to the 0 is not 1, but we're not worried about that here. What about a to the x over y? Yeah?
It's x minus y. Yeah, x minus y. Wait, I'm sorry. It's radical. The y is the index, and the x is the power.
Right? You can interpret it as that. Okay. But you get the idea. All the laws of exponents, they do apply if the base is the constant and the power is the variable. Okay. And things like the fact that something like a to the minus x is 1 over x to the a. So all those rules apply. That's the first thing you need to remember. So to actually deal correctly with exponential functions, you need to remember your laws of exponents, and you need to know how to apply them at any given time. Let's get some graphs. Let's say y is equal to a to the x. A is greater than 0. It's not equal to 1. Because, of course, if a is equal to 1, then this is always 1. That's just a horizontal line. We don't care about that. Okay? Does anyone actually know what the picture of this looks like? Just finger it. Yes, it's like that. What does it pass through here? 1, right? Because that's when the x value is 0. You plug in x equals 0, you get 1. It never actually touches the horizontal, but it gets closer and closer and closer and closer and closer, literally forever. And again, it's just like another function, so it is amenable to the transformation rules. So for example, if I have y is equal to a to the minus x, that means a reflection in the y-axis. Right? If I have y equals minus a to the x, that's a reflection of this guy in the x-axis. I have y equals minus 8 and minus x. That's a reflection of this guy in the x-axis. You can also be aware of the fact that again, this guy we can interpret as 1 over a to the x, or 1 over a raised to the x. So for example, if you wanted to graph 1 over 2 to the x, which I wrote here, its picture would actually look like this one. Okay. So those are all the graphs. You need to have these memorized. Have you guys done exponentials before in algebra? Okay, so again, it's a little bit of review. Right? But I'm reminding you of things that it's actually very important to know. We are going to cover, for example, one reason why knowing the pictures are going to be very beneficial to you. We're going to cover a topic called limits, and in limits, we're going to be doing a lot of calculations, and there are a lot of scenarios that can come up, and there are many scenarios in which knowing the picture of the function that you're working with can actually really help you a lot with figuring out what the answer is. So it's not just going to be about computation, it's going to be about you having a picture in your head while doing computations, and it will actually inform your decisions. Okay? And sometimes it can help you avoid computations altogether. Okay? But when we get to limits, you'll see that. But it is very important that you know what these pictures look like. Okay. What else do I want to tell you about exponential functions? I can get rid of these, right? You guys can probably redraw them here by heart anyways. That's good. I want to tell you guys about that right now. I will mention it. Let me mention it. There is a particular a value that is very important. Very important value in calculus. This is the value E. I know that's a letter, but it actually represents something. Okay, so just like how pi is a symbol that you know it represents some number out there, E is also going to be a symbol that will represent a number. This has value. It's approximately 2.718281. It's an irrational number, so the decimals will not repeat after a while. You can never actually fully write it down. So it's kind of like pi in that regard. It's a very famous irrational number, but it's particularly very useful in calculus. It's kind of like what pi is to geometry, E is to calculus, right? It's a number that's going to pop up all the time, and it's a very important number. Later, we will see E is actually equal to, there's a certain limit. Now, if you don't understand what this means, don't worry about it, because I will explain it at some point. But what you might want to think about where this number might show up is this guy here is actually the compound interest formula. With time set as 1 year and interest set at 100%. Right? And remember that compound interest, n is n equals number of times compounded per year. We're not really going to use this we're going to use this limit all the time, but we won't really use this interpretation all the time. But if you're curious as to where it comes from, that's kind of where this number arises. Right? It's basically comes from a thought experiment. This is the form that you'll get if you take the compound interest formula, plug in time equals 1 year, and set your R value equals to 1, which represents 100%. So you can imagine that you put $1 into a bank account that's paying you 100% compounded, and it's being compounded n times per year. This would be the formula that tells you how much money you have at the end of 1 year. Now, you can choose n to be any amount of times. You can apply the interest twice per year, biannually, so you plug in n equals 2, or 3 times per year, or 4 times per year, or 5 times per year, or 6 times per year, right? So now the thought experiment is, what if you can compound it at any interval of time, right? So it's not just, once per year, like 1,000,000 times per year, 1,000,000,000 times per year, 1,000,000,000,000 times per year, like an infinite amount of times per year, hence you get this guy. And it turns out that that will converge to this value. So that means if you start a bank account with $1 that pays you 100% interest rate and is compounded continuously, as they call it, at the end of 1 year you will have $2.72. So it's not like your money will grow infinitely even though you're getting 100% interest rate. That's one reason why it's interesting. But it was used a lot of times in theoretical economics and stuff like that. Like, what would happen if this we'd just keep the money growing forever, right? And this is useful in measuring that, right? So if you have the best possible scenario, 100% interest rate, and it's compounded like more than every second, more than every split second, that number will be this if you start off with $1. Okay, so that's kind of where this number arose for the very first time. But it's a very important number, and the reason is because there are a lot of formulas in calculus where having this number in it is going to make it a lot easier, and it'll naturally arise all the time. In fact, let me start it here. In fact, the function y equals e to the x is called the natural exponential function. Right? It's very natural for us to use it in calculus. We call it the natural function. That's how useful it is and how ubiquitous it is. It's a very natural thing to use for calculus, especially when you're dealing with exponents, right? And it's called the natural exponential. So if at any time a question talks about the natural exponential function, it's talking about an exponential function where the base is e, where it is this particular value. Remember? And at this point you probably won't know why I'm telling you this, but trust me, it's going to be important later. E to the x is a function. In fact, it's an exponential function by our definition. E by itself with no x's is a constant. Okay? So if you just see an e by itself, it's a constant. Okay? You see an e to the x, that's a function. That's going to be very important for us. When we get to calculus, things are going to be different whether you're dealing with a constant function versus some other kind of function. And a lot of times students mix these two up and they think, when they see this, they think of the function, but you really should be thinking of a constant. And if I put any number in here, like also, like e to the n, if n is a number, is also a constant. Of course, if e is a number, then if I take e squared, or like e squared, or e cubed, or e to the 1/2, or e to the pi, right? Whatever. If I put a number in the power, the entire thing overall is a constant. It's only a function if you have a variable in the power. And in that case, if there's a variable in the power, it is called the natural exponential function. one thing I want you to know is that I'm not just telling you about this random function. It is actually quite useful. Okay. Is there anything else let me make sure I didn't want to tell you anything else before that. I think we're sort of up to date. Okay, so there are many uses for an exponential function. So just as you know when you can use a linear function, you want to know when you want to use an exponential function. Exponential functions are often used in population models, right? If you're studying how population grows, whether it's a population of people, a population of bacteria, a population of rabbits, the function that would best describe such populations will have some variation of an exponential function in its own. Okay? A lot of financial models will use exponential functions, right? For example, the compound interest formula can be thought of as an exponential function in certain situations. Right? You can, if you're talking about radiation, also talking about exponential functions. So if you had someone so the people who are measuring, for example, the radiation levels in Chernobyl, at some point in their model, there's going to be an exponential function. Okay? Population, finance, exponentiation, radiation. It's all over the place, guys. There are tons of engineering applications that would use exponential functions. Not sure if you guys would see those at this point, but if you're an engineer or a math major, you'll come upon a subject called differential equations, which has a lot of applications, and the exponential function is all over in something like that. Lots more. Just trust me, they're all over the place. Let's talk about how do we know that we need to use an exponential model. So just like straight lines, there are certain clues that you would have to know that you need to look at this kind of function to figure out the answer. A lot of times it has to do with the topic. If I'm asking you a question about population, you kind of know, okay, it's going to be an exponential function. But other than that, here's what you can expect. One, again, you will be told to do so. So I can say, use an exponential function to model this data. Use an exponential function to relate this input to that output. Okay. 2, and here's where we can distinguish it from, for example, when we should use a linear model. You are measuring a quantity. That is changing by a fixed relative amount. On regular intervals. And by relative here I mean sort of percentage-wise. So if something is changing by, say, 2% of its value over time, that's an exponential. It's not changing by a fixed percent, because 2% will change as it grows. Okay? So that's called a relative amount. That actually finishes 1.5. Just in time. Yes. I just need one more word. Okay, so we'll pick up on Friday with this, and we can ask questions.
Oh yeah,